Okay folks, here we go. We're looking here at Winter 21 HL IB, HL I should say, question paper 2, and we're looking at question number 4 here. Now, on the screen as usual we've got the question paper with my worked answers, we've got the mark scheme, and we've got the data booklet. Obviously, if you're doing an exam, you'll be using the data booklet. Obviously, if you're marking your work, you'll be using the mark scheme. I thought we'd have everything up there just so we can give as full an impression of the work as possible. Let's go for it then. Let's scroll through to the correct section on nuclear physics. This is definitely an HL section. Okay, we're thinking about our, as we'll see later, with some calculations which involve the HL equations of radioactivity. Always a good idea, just have them in front of you. Okay, make sure that you are kind of making your life easy and not trying to dig anything out of your memory. Okay, remember, IB physics is not a memory test like, say, A level or a GCSE for that matter. Okay. First question, nice easy one to start us off, is to say what is meant by the binding energy of a nucleus. Now you should be aware that to pull the nuclei apart, to pull those nucleons away from each other, we need to do work, and that work is being done against the strong force. Okay, so that strong force that is going to cause us to input binding energy. And when we refer to the binding energy of a nucleus, it is the energy required to completely separate out those nucleons. Okay, only reason I would flag up this question at this stage is fairly standard definition, is that you may be asked what the average binding energy is. Okay, and that would be the energy required to separate one nucleon from the nucleus. i.e. you'll be taking the binding energy and dividing it by the number of nucleons, the number of protons and neutrons in the nucleus. So just be careful, make sure you read that question to start off. Okay, we're then asked to draw a graph, show the variation of nucleon number with binding energy per nucleon. That's the quantity I just mentioned before. Okay, you're not required any numbers, you wouldn't be required to remember this, absolutely not. But you are required to remember this standard shape which is on the screen. Now you can see there we've got a curve rising to a maximum, okay, and our maximum needs to be somewhere between 50 and 100. You should be aware that iron is our most stable element. It has a mass number, a nucleon number in the 50s. Okay, so we're expecting that greatest stability, okay, the greatest binding energy, in other words, to be somewhere between 50 and 100. And you can see that in the mark scheme, there's a nice kind of range that we're allowed in terms of making sure that we get that correct, between 50 and 100, okay? Hopefully you were able to get somewhere there. Okay, the reason, this is why I like showing my answers, okay, is because you'll notice there that there's no actual graph shown in your mark scheme. However, an example answer there would be quite useful. Okay, so we've done our graph, we've got it rising and then decreasing. Notice here there's a couple of little details. You're not worried about the starting point, and we're also not worried about the tiny maximum, which is at the alpha particle. Somewhere here the line isn't actually so smooth. No worries about that. Okay, we've identified with a cross where the region of greatest stability is. Okay, it's essentially at the peak of your graph. Okay, and then we're asked another little 1-mark question, which seems fairly innocent on the surface. Some unstable nuclei have many more neutrons than protons. Suggest the likely decay for these nuclei. Now, in this case, what we need to think about is that our different types of nuclei, our different types of decay, and how these affect the number of neutrons and protons. Now, you may be aware that the most stable, especially for low values of the most stable of our nuclei, tend to have balanced numbers of neutrons and protons. In other words, our unstable nuclei want to decay such that we lose neutrons and we gain protons. Okay, and the type of decay for which that happens is beta minus decay. In that sense, you should be aware that a neutron decays into a proton plus others. Okay, a neutron decays into a proton and an electron. Okay, that is the minus and the beta minus, and so we're left with more protons. And in that way, our nuclei are becoming more stable. Okay, so you notice again here, you're given a mark simply for saying beta minus decay. Okay, well, it would be good for you to have a little think about why that is as well, and that's because of that change in both the N and Z numbers, N being neutrons and Z being protons. All right, let's get into some maths now. So we've got plutonium-238 decaying by alpha decay, and we're told some following data. Now, be careful again, we are told the binding energy per nucleon, not the binding energy. That's important here, because we're going to use that binding energy to show that the energy released in the decay is about 6 MeV. Now, as you can see here, I've had a little bit of a nightmare, a bit of working, because I made a couple of mistakes as I did, and I want to show you those mistakes as I go. Okay, in order to get the binding energies here, to get the energy released, I should say, we need to know the binding energy, and by that I mean the total binding energy, not simply the binding energy per nucleon. Well, we know the binding energy per nucleon, then we need to calculate the total binding energy. All we do is multiply by the number of nucleons. So that is 238 in the case of plutonium-238 and 234 in the case of uranium. Now, you may not know that. However, we know that alpha has got a nucleon number of 4. And we also know that those numbers must add up. So 234 plus 4 is equal to 238. So, in each of my stages here, I'm taking the number given in the question, 7.568 in the case of plutonium, and multiplying by the number of nucleons in there. Okay, we've got a couple of numbers, and it's always a good idea to write those things down. Okay, now you can see the little mistake I've had here. I actually originally multiplied by the wrong number here. I multiplied by 92, which is actually the atomic number, and then I had a second. I thought, oh, hang on, made a mistake there. Okay, scored it out and put the right answer in. Okay, you can make mistakes, folks. Okay, physics exams are designed to be hard, and there's a lot of working out to do. So if you make a mistake, score it out, write the correct one, try and think about your work, and don't get too down if you do make a mistake, okay? In order to calculate the energy released, we're going to take, in my case, the energy of the original nucleus, that's the plutonium, and then take away the sum of the daughter products, which are the uranium, the alpha, and we end up with 10801 minus this whole load here with a minus 5.5. Okay, now in this question you were asked to show that it's 6 MeV. Well, 5.5 is close enough to 6. I mean, in my opinion, it's not very close. Okay, I wouldn't have been surprised if they'd said approximately 5.6 or even just approximately 5.5. Okay, but there you go. In IB's case, that's going to be close enough. Now, it says in the mark scheme, ignore the minus sign. Well, think about it this, if you've got a minus sign, as which I do, what you're saying is that it's energy released. And so that's actually okay. A minus sign doesn't matter here. You're really saying that the energy has gone down and therefore been released. Okay, so we've done some maths on the calculations of the energy. We're now going to look at the kinetic energy. Now, this is quite a tricky one because we're going to go back and think a little bit about our momentum. Okay, we know that the plutonium nucleus is at rest when it decays. So effectively, when we have decay in this way, we have what we call an explosion. In other words, we have something which was not moving decaying into to two things which do move. Now, it must be the case that those things have equal and opposite momentum. Okay, the total momentum has got to add up to be 0 before the collision, and so therefore the momentum Pu of the uranium, for example, is equal to the momentum, equal and opposite I should say, to the momentum of the alpha particle. Why is that important? Well, we can use our kinetic energy equal to P squared over 2m, and if you've forgotten that, then get filing through your data booklet, get trying to find those equations which we learnt a long time ago. Okay, we could have mv squared, okay, and then we've got p squared over 2m. Now, we want to find the ratio of the kinetic energies. Actually, that's the ratio of p squared over 2m to one another. Okay, and we find that because those two momenta are equal then and opposite, we square them, we get the same value, we can ignore them, and simply we're looking at the ratio of the mass of the uranium to the mass of the alpha particle, which comes up as 58.5, and that's the number which is in the answer scheme. And that's fairly well worked out here in the mark scheme. Okay, here's the tricky bit. This is the bit that, well, one of the tricky bits. There's a lot of nasty bits here. Oh, whoops, my scanning's gone a bit weird there. A lot of my students really didn't like this question, okay, which is about the energy and how it relates to power. And it's a really tricky one, but quite a nice one to see your understanding of physics. Okay, we've just worked out the amount of energy released in each decay. If we therefore know how many decays we have every second, then we can then say how much energy is released every second. And in other words, we're able to tell the power. Now this is a very involved, long, horrible calculation, as you can see on the screen. Okay, we know that each decay gives 5.5 mega electron volts. Now, in order to know the number of decays, that's really just the activity. And the activity is the product of the decay constant, which we're given in our question, and the number of unstable atoms. And that's fairly straightforward so far, but the problem is we don't know the number of unstable atoms. Okay, we know the mass of the pure plutonium-238. We don't know anything else. Well, we could go a little bit further, and we could decide to calculate the number of moles, which would be our small n, okay, and multiply that by Avogadro's number. The number of molecules is simply the number of moles times Na, Avogadro's number. We still aren't there yet, though, because we don't know the number of moles. We do know the mass, however, and you can see in green I've highlighted here. If we know the mass of a substance in grams, and we divide it by its molar mass, then we can get the number of moles. A key point here is we need to know the mass of our substance in grams and divide that by the molar mass in grams. And the molar mass in grams is 238 in this case. This very neat kind of way that we construct moles, etc. We know that the molar mass of any substance with mass number 238, okay, will have a molar mass of 238 grams. Okay, so this is where our calculation comes together. We've got our decay constant multiplying by the number of moles, which is the ratio of the masses, times the number of molecules in each mole, or number of atoms in each mole, times by the energy released by each decay, and then multiplied by E, because we're dealing in electron volts. Okay, and that all comes up to a very sensible, bizarrely sensible number of 18,364. In other words, 18.4 kilowatts. Whoa. Okay, hard work that. All right, lots to pay attention to. All right, let's have a look at the mark scheme to see if we can salvage any stuff. All right, okay. You can get marks here for telling me the number of nuclei present. Okay. You can get marks for talking about initial activity, okay, and you can get marks for showing the link there between the number of decays per second and also the energy released in every single decay, okay? So there's a lot to go on here, all right? What I would do in this case, if you're really not sure about how to do the working, then what you should be doing is at least laying down some of your thoughts, okay, and trying to process them in some way, okay. I know that this is actually quite a hard one, it can be very easily missed, all right, but you notice here that IB tries to be nice, they allow errors carried forward, okay. What this means, if you miss one of those numbers, okay, you may not get the marks. However, if you're starting to show that you're applying the right thinking, then you are going to at least get something for it, and something is absolutely better than nothing, okay? All right, very quickly on to the next one. The next one's a bit more straightforward, okay, but it's worth thinking about. And this is where I'm going to go back to our equations, okay? We were in the nuclear physics section. Here we go. Okay, now, as we've seen in the previous section, the power goes with our activity. As if we know the activity, then we know the power, as we know the amount of energy which is released by each of our decays. Okay, so we can actually kind of define our power as going with our exponential decay, just like every other quantity that we get in nuclear physics. So we can define P as a function of T to be some P0 times e to the minus lambda T. Now here P0 is simply the power you calculated in that first question. It's the initial power. So the power will also decay exponentially as well. We know the time here, we know the decay constant, so it's a case of simply multiplying through and getting an answer which is lower than the previous value, okay? Now, you'll notice my value is slightly different, okay? They got 18 kilowatts for their input energy, their input value there. Don't worry too much there. I've used the sort of raw data there, which will get a similar value. The important thing here is that it decreases not by very much, but by a certain amount over time, and that's what we'd expect as that fuel is being used up. Okay, back on to question D. Now, the nice thing about questions C and D is they are not related. Okay, and so therefore, if you found that question C was troublesome, well, question D hopefully gives you a chance to think about it. But again, there's some little tricks in this one as well. Okay, now in this one, we are combining two areas of physics, actually. We're combining our topic 12.1, the interaction of matter with radiation, with our topic 9, which is all about Doppler effect. And that, well, it apparently is about Doppler effect. Okay, you would be very tempted to think that we've got spacecraft moving away from the sun. And in that sense, therefore, we're going to have a Doppler shift. Okay, so we would think, well, we've got a Doppler shift, we're moving away, we should expect the frequency to change. Now, why is that important? If we scroll down to our interaction of matter with radiation, we can see here that we've got a frequency term, and we're being asked about the kinetic energy of emitted photoelectrons. Let's think about this. If Doppler effect applied here, then F would be going down, H is constant, and our phi, our work function, is constant, and so therefore we would expect the kinetic energy to decrease, and many students write that. Okay, you would notice that again in our paper. Now, you notice here, actually, IB is kind of nice, because they realize that a lot of students got confused by this question. So if you said that there's a change in frequency due to Doppler effect, therefore the energy will go down, you get a mark for that. You just don't get both marks. Okay, all right. The actual answer here is that it stays the same, because remember, when we do Doppler effect, when we do the Doppler effect of light, it is an apparent change. It's a change that we process. However, the energy, or the frequency of the light or the frequency of the sound isn't actually changing. It's just what we process. And so therefore, those photons of light that are being emitted are not changing their frequency. They will just be processed in our eyes as having changed their frequency. Therefore, the energy carried by each of those photons is the same, the frequency is the same, and therefore the kinetic energy is actually a constant value. Okay, again, a tricky question here, but you'll notice here that IB recognizes this in their mark schemes. They allow you some marks for getting it wrong, because they understand that it's very easy to get wrong. Okay, and I'll be honest with you, it took me some thinking as well, and I've been doing this for a while, so don't worry if you're only getting 1 mark on that question. Hopefully question 2 is a bit more straightforward, okay, because it's asking us what will happen to the rate at which charge leaves the metallic surface. Well, let's think about this. The charges each charge requires 1 photon in order to leave the surface. Okay, so 1 electron requires 1 photon. Now, if we move further away, then our intensity is going down. And that means fewer photons every second incident on the surface, and that therefore means fewer interactions. That therefore means there's less charge per unit time able to leave the surface, and therefore the rate at which they leave the surface is going to go down. Okay, and it would be my hope that that part of this question would be more easy to process than the top one, which is taking you down a little bit of a red herring with the Doppler effect. And I think it could be one of those things that the examiner doesn't really realize that when they set the question, and they may well be regretting it when they see some of the answers from the students. Okay, as we'll see in future videos, we don't always get it right, and what an examiner might think is obvious isn't, and we do have to take that into account whenever we're answering the questions. Okay, a long discussion there. Okay, I hope that the model answers are helpful. If anything, the mark scheme and just sort of what you're looking for in there is helpful too. If you've got any questions, as always, please ask.